Okay, let's go to the last topic for chapter 30 is gonna be LC circuit. Let's see what happens when we have a capacitor. We mentioned before that if this is the capacitor and this is the charge right of these two plates, if we connect these two plates by a wire where we discharge the capacitor, and that happens right away, right? Now, what happens if we add a resistor? Well, when we add a resistor, we can change the time for discharging this capacitor. It can go from a few seconds to minutes, right, to discharge this capacitor. That depends on the resistance and depends on the capacitance. Now, instead of this resistance, let's use a inductor. When we use an inductor, in this case, the charge just oscillate, right? The current oscillate. It goes back and forth through this two plate and through this inductor. Got it? Let's try to analyze this case using these figures. At the beginning, imagine that we have a capacitor is charged and we have the inductor and the circuit is opened. At this time, right, at equals 0, the current is 0. The voltage is the voltage of between these two plates, which is charged by the capacitance, and the energy is in the electric field, right? And the energy is equals to charge squared divided by 2C. Now let's close the circuit. Well, at the beginning we have the current increases. If the current increases, we have a change, right, in the current through this coil. Means that using the Faraday's law, we have a magnetic field created, right, that opposes the incoming magnetic field. So we have a magnetic field acting, let's say, in opposite direction. Perfect. But because the current is increasing, after a while it's gonna be decreasing, right? There's a point where it's maximum. And let's take this picture to be that case. In this case, the time is gonna be the total time, the period divided by 4, right? And the current is the maximum. And that happens when the voltage, right, through these two plates is 0. How we can create a voltage 0? Well, when these two have the same charge. If at the beginning this is 10 and 10, right? Right here now it's gonna be 5 and 5, right? Now we have these two are with the same potential, correct? And if these two are the same potential, well, the voltage to these two plates is 0. Correct, and the energy now is concentrated in the magnetic field, and that's the formula, right, for the energy gonna be inductance times the maximum current squared divided by 2. Okay, now current is going to the it's when it's maximum, but goes to the other plate, right? Is reversed, and then we have that later at t equals 1/2 of the total process, the current through this inductor or through this wire is gonna be 0. And again, the voltage, it goes to the these two plates. It's gonna be negative charge because we reversed, right, the polarity, negative charge divided by capacitance. And one more time, all the energy is in the electric field. It's equals to charge squared divided by 2C. And again, we repeat the process, correct? Then now the charge increasing, going to the left. We have an induced magnetic field opposing this charge or this current, correct? And that happens when t is equals 3 times the period divided by 4, and the current is gonna be the maximum. But it's gonna be negative because it goes now in opposite direction. Okay, and the same thing as before. Let's take the case when we have not potential difference between these two plates. Means we have the same amount of charges, positive and positive in both sides, positive and positive, correct? And well, there's no potential difference. Great. And again, all the energy now goes to the magnetic field, and that's again the formula. L current maximum squared divided by 2. Correct? And then we go back again, we go back and to the initial position, right? We get this plate to be positive, right, as the beginning, and the other plate to be negative. And all the energy is in the electric field. And that's the process, what is happening when we're dealing with LC circuit. So this is similar to a spring, right? When we have a spring, imagine this is the spring, this is the mass, correct? This is the equilibrium position, so we stretch it, we apply a force, and we release it. And what happens? Well, it start oscillating back and forth. This is a case one right here. Later, what happens? Well, all this energy, right, of the electric field goes to the magnetic fields. And what do we have? Well, that happens when the let's say the spring in this case is in the equilibrium position, right? Later, because of inertia, right, it keeps moving to the left, and that's the last position, correct, in this picture. Energy, like as you can see at the beginning, we have potential energies. Potential energy is converting to kinetic. In this case, everything is kinetic, right? And then goes to potential, and goes again to kinetic, potential, and so on. It goes back and forth, right? It's oscillating. The same thing happens, right, in this type of circuit. Later, right, the spring is gonna be, let's say, this position when x equals 0, right, and finally, right, at some distance from the equilibrium position. Correct? Perfect. Now let's try to find a relationship between this current, for example, and the time, right? How they are related. Okay, let's do it. The same thing right here. What should be at the beginning? The throw energy. Well, the throw energy is potential, right? So energy is equals to 1/2 k. Remember, this is the spring constant times x squared. Right here, all the potential is converting to kinetic, right? Like right here, all the electric energy is converted into magnetic energy. Magnetic energy right here, correct? So the same thing happens as using a spring. So now right here we have 1/2 mv squared, correct? Later what happens? Well, right here we have 1/2 kx squared, right, and so on. 1/2 mv squared and 1/2 kx squared. Right, that's the energy. The same thing happens, right, with the electric energy, magnetic energy. They switch each other as happening with a spring. Perfect. Now let's try to describe this circuit using Kirchhoff's rules. Let's do it. So in this case, let's see what happens when we close the circuit. And we use the loop rule. Okay, let's use the loop rule to find the equation that gives us the behavior for this simple harmonic motion. Okay, let's do it. So we have then this capacitor, and then we have this inductor right here. Okay, and now it's capacitance. This is a positive, this is a positive charge, right, a negative charge. So we have current in this direction. This is the inductor. Now when we use the loop rule, right, loop rule, what do we have? Well, we have that the voltage in the capacitor, which equals to charge divided by C, correct, minus the induced electromotive force in this solenoid, which is equals to L di dt must be equals to 0. Correct? Perfect. Now let's rearrange this in this way. Before that, look, the charge is moving, right? Remember the charge that moves is positive charge. It goes from here right to here. But in the capacitor, the charge decreases, correct? Of course, the current increases, but the charge right here decreases. Let's see what happens with this case when we have change in charge with respect to time. In this case, the change is negative because the charge is decreasing. So in this case, we have that the current is negative, right? This change. Now let's substitute this value right here. And what do we have? Well, we have that this is the charge divided by the capacitance plus L, which is the inductance, times the second derivative of the charge respect to time is equals to 0. Perfect. Now let's divide this by L, and what do we have? We have charge divided by LC plus the second derivative with respect to time is equals to 0. Correct. And this is similar to have, well, we can arrange it one more time in this way. Correct. The second derivative of the charge respect to time plus charge over LC is equals to 0. This is similar to the case when we have a simple harmonic motion. Remember, we found that the second derivative with respect to time plus omega squared x is equals to 0. Now, when we compare this to this, they have the same form. Now, when we compare this to this, we can see that omega squared is equals to 1 over LC. Means that omega, the frequency at which the charge oscillates, is equals to the square root 1 over LC, right? So we have omega equals to the square root 1 over LC. Perfect. Now, let's continue. Let's go back to this equation at the beginning, right? Where we have a harmonic motion, simple harmonic motion. Remember, we started with x. X is equals to a cosine omega t plus, right, plus a phase constant, correct? That's for x. What about in our case using the charge? Using the charge, we use charge is equals to because remember we use charge right here. I erased it from here. Is equals to maximum. This is the amplitude, correct? Time cosine omega t plus this change in the constant phase. Perfect. Now, what's next? Let's find the velocity. Okay, in x direction, for example, is equals to what? It's gonna be negative a omega sine, right, omega t plus phi. The same thing happens to the charge, right? Remember, the velocity is just the derivative of x with respect to time, right? Let's do the same thing for the charge. Let's derive the charge with respect to time. And how we call that? We call that the current at any instant. Perfect. And the current is gonna be equals to the same form. We're gonna be negative the total charge right here, omega sine omega t plus phi. Right, perfect. So we can represent also, well, charge. Let's start with charge right here. So we have charge is equals to maximum charge, right, cosine omega t plus phi. And we can also define current in this way, negative total charge omega sine omega t plus phi. Correct? Perfect. Now, let's erase this part. And let's continue the analysis. Great. We are right here. Now, let's go to the case when we have velocity, right, in the x direction. We found is equals to plus minus the square root k over m, the square root of a squared minus x squared. Let's do the same thing for charges, or in this case, current. So current, remember, is related to velocity when we're dealing with simple harmonic motion. So the same thing is going to be equals plus minus the square root of, remember this is omega, correct? It's going to be omega for us, it's going to be 1 over LC times the square root of, remember the maximum amplitude right here is Q, right, capital Q minus, right, small q, right? And we get the same form. Perfect. What else do we have? Well, now let's see how these quantities are related, right? We have, for example, mechanical quantities and we have electrical quantities. When we're dealing with X, right, in mechanical quantities, we are dealing with charge in electrical quantities. When we're dealing with velocity in X, right here, we're dealing with current, correct? And then when we are dealing with mass, right here, we're dealing with the inductance. When we're dealing with energy, 1/2 mv squared, right here is gonna be 1/2 Li squared. Correct? When we're dealing with a spring constant right here is gonna be 1/c. And now when we're dealing with elastic potential energy, 1/2 k x squared. Correct? Right here is gonna be 1/2 q squared, right, divided by c. Right? And these are again the relationship between these two quantities, right? These two systems when mechanical goes to electrical, and we're dealing with a periodic motion related to this RC circuit. Correct? Now, what happens when we're dealing with the energies, right? Energy is conserved, right? So the total energy in the electric field is going to be equal to energy, right, in the magnetic field, correct? Magnetic field. This one had max, right? When we had max, and what should be the energy in the electric field? Is going to be 1/2 charge squared divided by c must be equals to the induced, right? The energy in the inductor is gonna be equals to Li squared divided by 2. Correct? Now when we arrange this in this way, what do we have? We have that current, right, now it's gonna be max, because this is max. In this case, gonna be, because this is a maximum, gonna be max, correct? Perfect. So what should be the maximum current then? Is equals to charge, right? Charge divided by the square root of LC, right? LC. So that's gonna be the maximum current. Maximum current is equals to charge over the square root LC. Right? Well, this is again the analysis for the RC circuit. Right? Okay, how the charge, right, depends on the time, and also the current depends on the time, and the same thing when we're dealing with the amount of charges. Okay, perfect. Again, this is the case when we have not friction. Let's see the case when we add friction. How we can add friction to the system? Well, adding a resistance, a resistor. Let's do it. When we add a resistor, we create the LRC circuit. Now let's go to the LRC circuit. Right, okay, let's do it. LRC circuit means that we want to use friction, right? Or we are adding friction to this to the previous harmonic motion. Okay, and what do we have? Well, we have the same thing as when we have a spring with friction. We have a damped harmonic motion. Okay, let's do it. And let's see how we can describe this motion. It's very similar to the spring, right? Simple harmonic motion, very, very similar. Okay, now let's add the resistance. And what do we have? Well, we have this circuit, we have the resistance right here. Imagine it's open. Right here we have the inductor resistance, and right here we have the capacitor. At the beginning, again, it's gonna be charged, correct, as before, and the system is opened. Correct. We can use it that way, or we can use it this way. Okay, let's use it this way. Okay, perfect. What happens when we close the circuit? Okay, let's close the circuit. Of course, we have current through this loop. One more time, let's use Kirchhoff's rules as before. And what do we have? Well, we have that the voltage through these two capacitors, which is charged divided by C, minus what? Minus L, right? Changing current respect to time. Current minus what? Current times the resistance equals to 0. The same thing as before, right? The charge decreases. If the charge decreases, the change in charge is negative. So this change in charge respect to time, right, is gonna be negative. But what is this? This is again the current. One more time, let's substitute this value, correct, right here and right here. And what do we have? Well, we have that this is charge divided by the capacitance. In this case, it's gonna be plus because of the sign. Correct, it's gonna be L times the second derivative of the charge respect to time. Correct, plus the current, which is the derivative of the charge respect to times R is equals to 0. Correct. Now we can rearrange it. And what do we have? Well, we have, and we divide it by L, right? So what do we have? We have the second derivative of I respect to time, correct? Plus R over L, derivative of charge respect to time. This is the second derivative. Okay, plus charge divided by LC is equals to 0. We got this a similar form when we are dealing with simple harmonic motion, right? In simple harmonic motion, this is the equation that was found. This is m, the second derivative of x with respect to time, plus b, right, dx dt, correct, and then plus kx is equals to 0. Right, and the solution for this equation, correct, the solution for this equation, it was found to be x equals to amplitude e to the negative b over 2m times t times cosine omega prime t plus this phase constant phi. In this case, omega prime is equals to square root of k over m minus b squared over 4m. So if we compare this again, these two and also this one for charges, what do we have? We have that the charge is equals to a maximum, the amplitude times the times e to the negative r, so the resistance, divided by 2m times time, correct, times cosine omega prime times t times plus phi. In this case, omega prime is equals to the square root of omega squared, this omega right here, correct, minus r over 2l squared. Okay, and this is a solution for a this type of circuit. As you can see, this is a damped harmonic motion. when we have again resistance. The point is how it's gonna be then the oscillation. Well, the oscillation depends on what? Depends on the resistance, right? If the resistance is more resistant, well, imagine this is the springs oscillating up and down, right? Because it's damped, right? So it's gonna be decreasing, right, the amplitude, and disappears. If we increase the resistance in the circuit, we're gonna be decaying faster. If this is denser, right, maybe it's gonna be one or two in steps, correct? So in this case, we have three types of graphs that describe this motion, three special types, and that's related to the current, right? In this formula, we have that this is equals to 4L squared omega minus R squared divided by 4L, correct? The question is, this is equal to on this relationship, correct? Because it's a square. Also, we can use this relationship are related to 2L omega. Okay, because we can take the square on both sides. Now, what happens in this case? Well, what happens when R, the resistance, is larger than 2L omega, or when the resistance is the same as this quantity, right? These are the same, or when the resistance is less than this quantity. Okay, and we have these three special cases. Let's try to represent these three special cases for this circuit. Perfect. We have, for example, this case. This is the charge right here. This is the charge, and this is time, correct? And this is one case like this. Okay. In this case, we have that the resistance is not too much, right? The charges still oscillate, right? Because of resistance, the amplitude decreases and disappears, right? This is again special case, and this is when or the resistance is less than this quantity, 2L omega. Correct, and this is called the underdamped situation. Underdamped. Now let's go to the case when R is the same as this quantity, or R is greater than this quantity, right? When the friction gets big friction, well, we don't have oscillation because of friction, correct? And we can represent these two cases in this way. One more time, this is time and this is the charge. And now we go one of the cases gonna be this one like this, approaching to 0, and the other one will never reaches 0, the equilibrium position. 0 in this case is the equilibrium position. Okay, perfect. And this is the case when R is larger than 2 omega times L, correct? And this is the overdamped. This is overdamped condition. Okay, perfect. And then we have the overdamped. Okay, and then we have this case when R is, this is the resistance, is equals to 2 omega L, and this is the case for critical damped. Critical damped, right? Critical damped. Correct. Again, and that's what's happening in circuit. We have oscillations. Okay, when we have only LC circuits. Now we are resistant. Well, the oscillation decreases depends on the amount, on the size of the resistance. We have three special cases, right, that are described in this circuit. Correct. Okay, well, with this, we'll finish this chapter. And see you in the next chapter, chapter 31. Wait, thank you. See you later.